Imagine an engine that has powered human progress for over half a century. It's not made of steel or pistons, but of silicon and light. For 50 years, this engine followed a single magical rule. Every 2 years, it would double in power for the same price. This wasn't a law of physics, but it might as well have been. We called it Moore's Law. It gave us supercomputers, the internet, the phone in your pocket. But now, that engine is sputtering. It's overheating. And it's starting to break the very laws of physics it was built on. The age of silicon is ending, and the race to build what comes next has already begun. In 1965, Intel co-founder Gordon Moore made an observation that would become a self-fulfilling prophecy for the entire technology industry. He noted that the number of transistors, the tiny electronic switches that are the building blocks of modern computing that could be placed on an integrated circuit, was doubling roughly every 2 years. This relentless pace of miniaturization became the drumbeat to which the digital world marched. Each generation of chips became exponentially more powerful, enabling waves of innovation that have fundamentally reshaped modern life. For decades, this progress felt effortless, almost inevitable. But behind the scenes, the economic and physical costs of maintaining this pace have been spiraling. Moore's law was always more of an economic observation than a physical one, and the economics are becoming punishing. The research and development, manufacturing and testing costs for each new generation of chips have increased steadily. A state-of-the-art semiconductor fabrication plant, or fab, can now cost over $30 billion to construct. Inside these fabs are the most complex machines ever built, extreme ultraviolet, or EUV, lithography systems. These are the only tools capable of etching the impossibly small circuits on today's most advanced chips, and a single machine costs upwards of $380 million. This immense financial barrier is the first sign that the engine of Moore's law is running out of fuel. But the more profound limits are not financial. They are baked into the laws of physics itself. The silicon chip has run into 3 fundamental walls. The first is the power wall, a thermal barrier born from the end of a principle known as Dennard scaling. In 1974, IBM researcher Robert H. Dennard observed a beautiful synergy. As transistors shrank, their power density stayed constant. This meant that as engineers packed more and more transistors onto a chip, the total power consumption and heat generated didn't skyrocket. It was like building a city of skyscrapers, where each new building added didn't increase the city's total power bill. This elegant scaling relationship was the secret sauce that made Moore's law so effective for so long. But around 2006, this free lunch ended. As transistors became atomically small, a phenomenon called leakage current became a dominant problem. The components became so tiny that they started to leak electricity even when they were switched off, wasting power and generating excess heat. The more transistors you packed in, the hotter the chip became, threatening a thermal runaway that could destroy the circuit. The city of skyscrapers had become so dense and its walls so thin that the air conditioning couldn't keep up. The city started to overheat. This is the power wall, and it's the reason CPU clock speeds have stagnated for over a decade, forcing chip designers to pivot to multi-core processors as an alternative path to performance. The second barrier is the quantum wall. A transistor is fundamentally a switch. In its off state, a physical barrier, a layer of insulating material, prevents the flow of electrons. But when that barrier shrinks to a thickness of just a few atoms, around 1 nanometer, the bizarre rules of quantum mechanics take over. Electrons, behaving as waves, can do something impossible in our macroscopic world. They can tunnel through a solid barrier they don't have the energy to overcome. It's as if they can ghost through a wall. This quantum tunneling is a disaster for a transistor. It means the switch is never truly off, leading to computational errors, increased power drain, and yet more heat. This effect represents the fundamental lower limit on how small a traditional silicon transistor can be made. chipmakers have waged a heroic battle against this quantum leakage, developing new transistor structures like FinFETs and using better insulating materials like hafnium oxide instead of silicon dioxide. But these are workarounds. Ultimately, it is a fight against the very nature of physics at the atomic scale. The third and final barrier is the traffic jam, more formally known as the interconnect bottleneck. A modern chip isn't just a collection of transistors, it's a metropolis of billions of them, all linked by a dizzyingly complex network of microscopic copper wires called interconnects. As transistors continued to shrink, these connecting wires had to shrink as well, creating two crippling problems. First, electrical resistance increases as a wire gets smaller. It's simply harder to push electrons through a narrower pipe. Second, as these tiny wires are packed closer together, they begin to interfere with each other through an effect called parasitic capacitance, causing signal delays and leakage. The result is a massive traffic jam on the chip. It doesn't matter how fast the individual transistors can calculate if the information can't get to and from them efficiently. The communication delay between components is now becoming as significant, or even more so, than the computation delay itself. These three walls, power, quantum, and traffic, are not separate crises. They are a cascading failure mode, all stemming from the singular pursuit of miniaturization that defined Moore's law. The very strategy that drove 50 years of success has become the source of its demise. The predictable, 2-year cadence of advancement that the entire tech world was built upon is over. This has created a strategic vacuum, a moment of profound uncertainty, where the old rules of the game no longer apply. It is an opening for disruptive, non-traditional approaches to computing to emerge. And it is this physical crisis that has set the stage for a new geopolitical one. The global semiconductor industry can be imagined as a vast, complex game board. It is a model of globalization, where no single country possesses every piece of the puzzle needed to create an advanced chip. Instead, it relies on a multi-step, globe-spanning value chain, integrating the unique strengths of the US, Taiwan, South Korea, Japan, Europe, and China. However, on this board, a few key squares act as choke points, nodes so critical that whoever controls them effectively controls the game. For the production of the world's most advanced logic chips, 2 choke points stand above all others. The first is a Dutch company called ASML. They are the sole manufacturer of extreme ultraviolet, or EUV, lithography machines, the most complex and precise manufacturing tools ever created. These machines, the size of a city bus and weighing over 150 tons, use incredibly short wavelength light to etch the microscopic circuit patterns onto silicon wafers. Assembling a single unit takes 250 engineers 6 months, and the latest models cost over $380 million each. ASML holds a complete monopoly on this technology. If you want to build a leading-edge chip, you have no choice but to buy from them. The second choke point is the Taiwan Semiconductor Manufacturing Company, or TSMC. Even with ASML's magic wand, the process of fabricating advanced chips at massive scale with commercially viable yields is an art form perfected by TSMC over decades. Today, TSMC produces over 90% of the world's most sophisticated microchips and controls around 67% of the market for advanced nodes below 7 nanometers. They are the indispensable master builder for virtually every major tech company, from Apple to Nvidia. For years, China has been a crucial player on this board, but primarily as the world's largest consumer of semiconductors, purchasing more than half of all chips manufactured globally. However, its ambition, laid out in plans like Made in China 2025, has been to achieve self-sufficiency and eventually leadership across the entire value chain. This ambition ran headlong into a new American strategy. Beginning in October 2022 and progressively tightened since, the United States has weaponized these choke points. A series of sweeping export controls were implemented with the explicit goal of denying China access to the tools and technologies needed to produce advanced semiconductors. While Chinese firms can still purchase older deep ultraviolet (DUV) lithography machines, they are strictly banned from acquiring the state-of-the-art EUV systems from ASML required for manufacturing chips at the leading edge. This move effectively puts a hard cap on China's technological advancement in the silicon race. According to ASML's own CEO, this ban is profoundly effective, setting China's domestic chip industry back by an estimated 10 to 15 years. This American strategy is more than just a blockade. It is a calculated campaign of economic and scientific attrition. The US and its allies understand that replicating ASML's technology is a near impossible task in the short term. It is the product of a globalized supply chain and decades of accumulated, irreplaceable expertise. By denying access, Washington forces Beijing into a difficult choice. Either accept falling permanently behind in the foundational technology of the 21st century, or pour hundreds of billions of dollars and its best scientific minds into a desperate attempt to reinvent a technology the West has already perfected through global collaboration. It is a strategy designed to bleed a competitor's resources and divert them from other innovative pursuits. However, this very strategy, in its effectiveness, has created the single greatest incentive for China to stop playing the game altogether. For years, Chinese leadership has identified its dependence on foreign core technologies as a critical national security vulnerability, a problem of being stuck in the neck by foreign powers. The US sanctions transformed this theoretical weakness into a painful, immediate reality. Faced with what is now an unwinnable game on the silicon board, the most logical strategic response is not to keep playing, but to flip the table and start a new game with entirely different rules. This intense geopolitical pressure has become the direct catalyst for China's high-risk, high-reward leapfrog strategy. What if you could change the game entirely? What if the future wasn't written on silicon? This question has led researchers to a new frontier of materials science, a realm of substances so thin they challenge our very definition of a three-dimensional object. The story of these 2D materials begins, improbably, with a roll of Scotch tape. In 2004, physicists Andrei Geim and Konstantin Novoselov at the University of Manchester used the humble adhesive to peel away layers from a block of graphite. They repeated the process over and over until they had isolated a layer so thin it was just a single atom thick: graphene. This discovery, which won them a Nobel Prize, opened the door to a whole new class of materials. A 2D material is a crystalline solid consisting of just a single layer of atoms. While they obviously exist in our three-dimensional world, their height is practically zero, and their unique properties are governed by the physics of 2 dimensions, as electrons are confined to move only along the flat plane. Graphene, a sheet of carbon atoms, is 1,000,000 times thinner than a piece of paper and is believed to be the strongest material in the world. But for all its marvels, graphene has a fatal flaw for electronics. It lacks a natural band gap, making it difficult to use as a transistor. This is where another member of the 2D family enters the story: indium selenide, or InSe. Dubbed the golden semiconductor by researchers in China, it is a layered material that, like graphene, can be exfoliated down to an atomically thin sheet. But unlike graphene, InSe is a natural semiconductor, and it possesses a unique combination of superpowers that make it a compelling alternative to silicon. First is its incredible speed and efficiency. InSe boasts exceptionally high electron mobility, a measure of how quickly an electron can move through a material under an electric field. Experimental values have exceeded 2,000 square centimeters per volt per second, significantly higher than silicon's mobility of around 1,400 square centimeters per volt per second, and far superior to most other two-dimensional materials. If electrons in silicon travel down a bumpy country road, in InSe they move on a frictionless superhighway. This translates directly to faster transistor switching speeds and higher performance. Furthermore, because the material is atomically thin, a transistor's gate has excellent electrostatic control over the channel, drastically reducing the power leakage that plagues tiny silicon transistors. This property directly attacks the power wall, with some research suggesting InC could enable memory technologies that consume 1 billion times less power. Second is its natural talent for light. InC has what is known as a direct band gap. In simple terms, a band gap is the energy an electron needs to jump into a state where it can conduct electricity. In an indirect band gap material like silicon, an electron needs not only the energy from a photon of light, but also a kick from a lattice vibration, a phonon, to make the leap. This two-step process is inefficient. In InC, the jump is direct. An electron can absorb a photon and jump straight into a conductive state. The process is highly efficient in both directions. To use an analogy, silicon is like trying to throw a ball into a moving basket. You have to get the timing just right. InC is like throwing it into a stationary one. It's far easier. This makes InC a perfect material for optoelectronics, devices that merge light and electricity, such as highly sensitive photodetectors, solar cells, and, crucially, on-chip optical interconnects that could solve the traffic jam bottleneck by replacing slow electrons with signals moving at the speed of light. For all its promise, InC has long been confined to the laboratory. The Scotch tape method produces pristine but tiny, irregular flakes, unsuitable for mass production. Other methods like chemical vapor deposition, CVD, have struggled to grow large, uniform films without defects, and most critically, have failed to consistently maintain the perfect 1-to-1 atomic ratio of indium to selenium required for optimal performance. This production challenge was the great barrier preventing InC from becoming a viable technology. That barrier may have just been broken. In July 2025, a team of researchers from Peking University and Renmin University of China published a landmark paper in the journal Science. They announced a novel solid-liquid-solid strategy for mass production. The process involves heating an amorphous or non-crystalline film of indium selenide alongside solid indium in a sealed environment. The vaporized indium atoms create an indium-rich liquid interface at the film's edge, which then acts as a catalyst, gradually converting the amorphous film into a large, high-quality, single-crystal wafer. This ingenious method solves the critical stoichiometric problem, ensuring the perfect 1-to-1 atomic ratio is maintained across a large area. The result of this breakthrough was the successful production of a uniform 5-centimeter diameter InC wafer, on which the team fabricated large-scale arrays of high-performance transistors. As one of the lead researchers stated, this has overcome the critical bottleneck in the transition of indium selenide from laboratory research to engineering applications. This achievement is more than just a scientific success. It's a profound strategic signal. The global semiconductor industry is built on the circular wafer. All the multi-billion-dollar machines in a modern fab are designed to process them. By explicitly focusing on creating a wafer, the Chinese team demonstrated that their goal is not merely academic discovery, but the creation of a new industrial platform. They are speaking the language of manufacturing, signaling to the world that they believe they have found a scalable path forward. This material doesn't just offer an incremental improvement over silicon. Its properties directly address the 3 physical walls that are blocking silicon's path, offering a potential way to leapfrog the limitations of the past and build the foundation for a new technological future. The convergence of a physical crisis in silicon, a geopolitical blockade by the West, and a materials science breakthrough in Beijing forms the basis of a daring strategic play by China. This is not a conventional attempt to catch up in an established industry. Instead, it is a high-stakes leapfrog gambit, an effort to sidestep the current technological paradigm entirely and establish a new one where China can set the rules. A leapfrog strategy, in the context of technological development, involves a latecomer deliberately choosing a different, often more radical, technological path rather than following the incremental steps of the industry leader. For decades, China pursued a path-following strategy in semiconductors, attempting to replicate the West's silicon-based ecosystem. This approach yielded only limited success, largely because the knowledge required for advanced silicon manufacturing is highly cumulative, built up over more than 50 years of trial and error. The US export controls made it clear that this path was not only difficult, but now politically impossible. The INSEE breakthrough offers an alternative. It represents a bet on shifting the nature of the competition. Instead of a game of immense capital investment and decades of accumulated know-how in silicon, a game where the West holds an insurmountable lead, China is attempting to change it to a game of materials science and novel device physics, where a single breakthrough can reset the entire playing field. By championing a new material standard, China aims to make the West's most powerful strategic assets, the EUV and foundry choke points, less relevant, or perhaps one day, obsolete. If this gambit were to succeed, the implications would be world-altering. China could establish a new, parallel semiconductor ecosystem, complete with its own design tools, materials, and manufacturing processes, all free from US control and influence. This could lead to a bifurcation of the global technology landscape, creating a silicon sphere of influence led by the US and its allies, and a golden sphere centered around China's new material platform. The world would face two distinct and potentially incompatible technological standards. This strategy aligns perfectly with China's overarching national doctrine of military-civil fusion. The development of a secure, sovereign, and advanced domestic semiconductor base is not merely an economic ambition. It is a core national security imperative. The US sanctions demonstrated in the starkest possible terms the risks of foreign dependency. A successful leapfrog to an INSEE-based technology would provide China with a sovereign technological foundation to power its future economy, its artificial intelligence ambitions, and its military, all independent of foreign pressure. More profoundly, a successful leapfrog would not just grant China technological independence, it would invert the global dependency model. Today, the world, including China, is dependent on the technological choke points controlled by the West. In a future where next-generation optoelectronics or ultra-low-power AI chips rely on INSEE, the best, or perhaps only components, might be sourced from China. This would give Beijing the very same strategic leverage over global supply chains that the United States currently wields against it. This is the ultimate, long-term prize of the golden semiconductor plan. While the strategic vision for a new semiconductor paradigm is compelling, the path from a laboratory breakthrough to global industrial dominance is fraught with immense and sobering challenges. The leapfrog gambit is a high-risk endeavor, and a reality check reveals several mountains that China must climb. The first and most fundamental hurdle is the raw economics of the materials themselves. Silicon is the second most abundant element in the Earth's crust, making it incredibly cheap. Indium and selenium, by contrast, are rare and expensive. Indium's abundance is comparable to that of silver, and it is primarily sourced as a byproduct of zinc refining. This inherent scarcity and high cost present a formidable barrier to replacing silicon in the multi-trillion-dollar mass market for electronics. As the table illustrates, while INSEE offers superior performance characteristics, its material cost and the sheer scale of the existing silicon ecosystem present monumental challenges to its widespread adoption. Even if the material costs could be managed, a new semiconductor material is only the first piece of a gigantic puzzle. A complete industrial ecosystem must be built around it. This includes developing entirely new electronic design automation (EDA) software tailored to the physics of 2D transistors, inventing and scaling new manufacturing equipment, establishing a complex global supply chain for precursor chemicals, and training a massive workforce of engineers and technicians with a completely new skill set. The West took over 50 years to build this ecosystem for silicon through market-driven, globalized collaboration. China is attempting to replicate this feat for a new material, largely on its own, and on an accelerated timeline. The scale of this challenge cannot be overstated. The breakthrough at Peking University produced a 5-centimeter wafer. The current industry standard is the 300mm or 12-inch wafer. Scaling up production by this magnitude while maintaining quality and achieving high yields is a monumental engineering task. Furthermore, 2D materials are notoriously difficult to work with. Achieving low-defect, wafer-scale synthesis and creating clean, stable interfaces between the two-dimensional material and other components like metals and dielectrics are persistent challenges that remain largely unsolved at an industrial scale. The target China is aiming for is also a moving one. The silicon industry is not waiting to be disrupted. Faced with the end of traditional scaling, it is innovating in other directions. Advanced packaging techniques like heterogeneous integration, or chiplets, allow designers to stitch together multiple smaller, specialized chips into a single, powerful package. 3D stacking allows for vertical integration, creating denser and more efficient processors. These innovations are extending the life and performance of silicon technology, raising the bar that any new material must clear to be competitive. The gap between a promising laboratory result and a commercially viable product is vast. The exceptional performance of INSEE has often been demonstrated on tiny, mechanically exfoliated flakes in pristine lab conditions. Historically, the performance of larger grown films has not been able to match these results due to defects and impurities. Skeptics rightly question whether the performance demonstrated on a 5-centimeter wafer can be maintained and replicated across millions of units in a commercial fab with high reliability and yield. Many experts believe that due to these challenges, INSEE and other 2D materials may be reserved for niche, high-cost applications such as specialized military sensors or scientific instruments, rather than replacing silicon in mainstream computing. This points to the greatest risk for China's strategy: not outright failure, but a Pyrrhic victory. If, after investing hundreds of billions of dollars, INSEE only proves viable for a small, specialized market, China will have succeeded in dominating a technological niche, while the multi-trillion-dollar global market for consumer and enterprise computing remains firmly in the silicon sphere. Such an outcome would represent a massive misallocation of national resources, leaving China even further behind in the mainstream technological race. However, even a partial success would have significant spillover effects. The massive state-led push to build this new ecosystem will inevitably generate valuable knowledge, patents, and a highly skilled workforce in materials science and advanced manufacturing, assets that will undoubtedly benefit China's broader high-tech ambitions, regardless of the ultimate fate of the golden chip.